Hi everybody. In this lecture we're going to start talking about molecules, and over the molecules chapter, which is chapter 9 in your textbook, we're going to talk about bonding of molecules, and that's the lecture today. We're going to talk about rotational and vibrational spectrums from molecules, and then we're going to talk maybe about lasers a little bit. So this one is about bonding, covalent bonding, and an extreme example of that is ionic bonding, and that's really what this lecture will be about. I have on the screen a picture of Linus Pauling, who did a lot of work initially in the early days of quantum mechanics on molecules. And I think he was the first one to measure electron affinities very well, for example. So he was also a great lecturer. He was one of the few people to win 2 Nobel Prizes. One was the Nobel Peace Prize because he was very concerned about nuclear weapons, and he was an activist against nuclear weapons. So he lived to a ripe old age. He advocated extreme amounts of vitamin C when he was older. Took a lot of criticism for that. So we're going to talk about bonding of between molecules. We're going to talk about one of the simplest molecules, a diatomic molecule. Only way it could be simpler is if the 2 atoms in the diatomic molecule were the same. So first we're going to talk about lithium chloride as our example of ionic bonding. So just to give you a heads up of what we're going to be looking at, we're going to derive a model for this potential curve here for the bonding between 2 atoms. And on this axis, the horizontal axis, is the distance between the 2 atoms. So keep that in mind. So as they get closer, at some distance between them, there's an equilibrium point, and that's where there's really no net force there. So we're going to try to come up with this model, and that's what we're going to do today. Okay, so let's try to come up with a mathematical description of molecular bonding. So the kind of bondings that we're going to look at, they have names such as covalent bonding, and then a form of covalent bonding is ionic, sort of an extreme form. And then we're also going to talk about van der Waals forces, van der Waals bonding, and hydrogen bonds. So first we're going to consider ionic bonding because it's a form of bonding we can come up with a mathematical model for. So let me talk through the model first. The model is this, that we have 2 atoms that are neutral atoms. So how are they going to combine? Well, what we do is we add on an extra electron to one and take off an electron from the other. Some atoms want to accept an electron more than they want to give one up. The types of atoms that will form these type of bonds, the ones that will tend to give up an electron are maybe hydrogen, lithium, for example. The ones that want to, so if you realize these are in the first column of the periodic table, and they have, for example, hydrogen and 1s. For lithium, it has the 2s, 1 electron. And then over on the other side of the periodic table, you have something like chlorine, or fluoride, which has for example, chlorine has a 3p5, and we really know I'd really like to have 3p6. That would be like a noble gas. So these tend to want to grab the electron, and they'll take it off of the ones over here. So ionic bonding is a form of covalent bonding, but the electron really stays around one of the atoms more than the other. It's not really shared equally in any sense of the word. So now for a model, how we're going to model this type of bonding. We're going to start with the fact that we create the ions first. So this is going to be the total energy, total potential energy for our molecule. And it comes from, well, first we have to have some energy to create the ions. Secondly, we have a potential energy between the ions, a Coulomb potential, so that's negative. And then we have, maybe if they get too close, we have some repulsion term. So I'll call it. So this is going to be our model. So there'll be a repulsion between the term between the atoms, because if they get too close, then the protons, or the positive charge of the nuclei, repel each other. So again, now I will say that the repulsive term, so these are a distance r away, the repulsive term, we'll let it equal some constant inversely proportional to the distance between the nuclei to some power. So if this is the total energy, potential energy, we have some energy just to create it as an ion, or to create our two ions. And then we have an attractive Coulomb potential that goes towards 0 at infinity. And we have a repulsive term that gets really big as they get really close, then dies off pretty quickly towards 0. And then all of those terms together, when you combine them, we're going to get something that looks like this. Now, this energy from the minimum up here to 0 energy, this is called the dissociation energy. And this is the distance between molecules along that axis. So, right here at the minimum, this is going to be, we'll call that R naught. That's the equilibrium distance between the atoms that compose the molecule. So now here's our model for the energy. Let's first figure out what energy is required to make our two ions. So we said chlorine, 3p5 is the valence electron. It wants to really gain another electron. So one of the first scientists to actually measure accurately electron affinities was Linus Pauling. And for chlorine, the electron affinity is 3.61 eV, so it means to add on that extra electron to make it a negative ion, it takes negative 3.61 electron volts. It wants to do that. So let's also look at lithium. So our molecule that we're going to model is lithium chloride. So lithium, which has a 2s electron, so the ionization potential for lithium, which I know you know what that is, that's the amount of energy required to remove the valence electron. It is 5.39 electron volts. So that means the total energy required to make these two ions is 5.39 eV minus 3.61 eV. So we get positive 1.78 electron volts. Now we need a couple of other things to finish off our model. So we have the ion energy. We need something for the potential energy, and we need to find this B, this constant, and this M. Now, a couple of things that we can look up thanks to a good chemist. We can find what that equilibrium distance is between the lithium chloride atoms. And it turns out, if you look it up in the Handbook of Chemistry and Physics, it's 0.202 nanometers. So that's going to help us. The other thing that's going to help us is we know what this total energy is at that equilibrium distance, that dissociation energy. That energy from 0 to the minimum. So that's the total energy of this thing at that equilibrium point. That dissociation energy turns out to be negative 4.86 electron volts. So we know what the equilibrium distance is, and we know this is negative 4.86 eV equals the ion, the energy to create the ions, 1.78 electron volts, minus K, which is 9 times 10 to the 9. K is the constant in the Coulomb force law. Newtons times meters squared over Coulomb squared. E squared over R naught plus B over R naught to the M power. We can calculate this easy enough. I'm just going to get the magnitude there. And that turns out to be 7.13 electron volts. So now we have negative 4.86 electron volts. The dissociation energy equals 1.78 electron volts minus 7.13 electron volts plus this. Okay, so our goal now is to find this constant B and this M. So we have this equation, but we have these two unknowns. So what else can we use? We can use the fact that if this is our potential, at the equilibrium point, the force, which is the gradient, negative the gradient of the potential, is 0 at the equilibrium point. So if we look at our potential, we have just a constant energy it costs us to make our ions. Then we have this Coulomb potential, and now we have the repulsive term. If I take the gradient of this, I only take the gradient of these two. One's going to be positive and one's going to be negative. I'm going to set them equal to each other. So and I'm going to evaluate it at R equals R naught at the equilibrium point. So what this is going to imply is I'm going to have a Coulomb force must be equal to this if there's no net force. Now if I go back to this, if I solve for the repulsive term, I'm going to get, it's going to be equal negative 4.86 minus 1.78 plus 7.13 EV. So I am going to get that to come out to be a positive 0.49 EV. So we'll use that too. Now I'm going to rewrite this side right here. The potential energy at the equilibrium, the Coulomb potential energy. Remember, I know what R naught is. It's R naught is 0.202 times 10 to the negative 9 meters. That's going to turn out to be, well, if I put the negative sign in, it'll be a negative 7.13 electron volts, and you can double check that. So I go back up here. I'm going to come down here. I'm going to rewrite that as K E squared over R naught times 1 over R naught. That's the Coulomb term. Equals MB R naught to the M 1 over R naught. So the R naughts can get canceled out. And I know what this is. Negative 7.13 electron volts. Well, I'm just worried about the magnitude there. Equals. So now I have this equation, and if you remember, I have this. So what does that give me? That's going to imply that 7.13 electron volts equals M times 0.49 electron volts, since this is this. So I get M is 14.6, and I'll round that up to 15. So there we go. Now I just need to get B, but I have B over R naught to the 15, is 0.49 eV, so that V is. So now I have my model for lithium chloride. The potential energy, so a function of R, is equal to the 1.78 eV, that's the ion energy, then minus K E squared over R, plus R naught to the 15, 0.49 eV, over R to the 15. So you can see this is not going to matter until it gets very close. This term is going to dominate for most regions. But to do this, we needed that the dissociation energy, which was the potential at the equilibrium point, that was a negative 4.86 eV, and we needed that equilibrium distance between the atoms. Okay. So there's